High in the foothills of the Little Drakensberg Mountains, right on the border between the Free State and KwaZulu-Natal, lies the INGULA hydroelectric power project designed to generate 1,330 megawatts of electricity. This is the Electrical Generating Authority of South Africa, Eskom's new pumped storage scheme, which will in due course be put into operation to generate much needed electricity in times of peak demand. Lying some 23 kilometers northeast of Van Rieenen and 40 kilometers northwest of Ladysmith, the pumped storage scheme consists of an upper and a lower dam with an underground power station connected by a series of tunnels over 9 kilometers long. Both the Upper Bedford Dam, situated 1,760 meters above sea level, and the Lower Bramhoek Dam will contain approximately 22 million cubic meters of water. During times of peak electricity consumption, water will be released from the Upper Bedford Dam to rapidly flow through pump turbines to generate the electricity. There are 4 reversible pump turbines housed in a gigantic underground turbine hall. The turbine hall measures 140 meters in length with a width of 40 meters. Each turbine is capable of generating 333 megawatts of electricity. Once the water has passed through the underground turbines, it will flow through the draft tube and tail race tunnels into the Lower Bramhoek Dam. During times of low energy demand, such as on weekends and at night, the reversible pump turbines will be used to pump the water back up into the Bedford Dam, ready for use when the next peak energy demand strikes. Construction of the project started in 2005 with a 1.2 kilometer exploratory tunnel which was completed in June 2007. Priority was given to the road's infrastructure as heavy loads of material and equipment would be brought onto the various sites by road. Construction of the road started in January 2007 and was completed in June 2009. This included the construction of a pass to the top of the escarpment. Meanwhile, construction of the 2 dams, Bedford and Bramhoek, was forging ahead as their completion and commissioning ahead of the tunnel and turbine infrastructure was deemed important. Both dams are now complete and collection of water in the Lower Bramhoek Dam began in November 2010. Work on the intake canal and head race at the Upper Bedford Dam is going to schedule. The main tunnelling contract was awarded to CMI, a consortium of South African and Italian companies. The total length of project tunnelling is in excess of 14.5 kilometers with 1.2 kilometers of vertical shafts. Most of the tunnels were constructed using drill and blast methods, and the vertical shafts were raise bored. The elevation difference between the upper and lower dams is 470 meters, and the water will flow to the turbines through twin low-pressure head race tunnels and high-pressure inclined shafts before each of the tunnels bifurcates into the high-pressure penstocks leading to the turbines. The initial section of the low-pressure head race tunnel is lined with concrete, and as the momentum and pressure of the water increases, the tunnel is lined with steel. 4 draft tubes, which ultimately converge into a single tail race tunnel, will carry the water from the turbines to the Lower Bramhoek Dam. To withstand the very high pressure of the water, it is necessary to line the head race tunnels and inclined shafts and pressure tunnels with a continuous steel lining designed to withstand internal pressures of up to 72 bar. Bifurcation and external pressures range between 10 bar to 58 bar. To achieve this, a very high-strength quenched and tempered steel was chosen to be utilized for the project. CMI, the main contractor, recognized the difficulties in the logistics, manufacturing and installation of the steel tunnel linings and set about identifying a company with the insight and experience to overcome these challenges. WHESSOE SDN BHD, based just outside Kuala Lumpur in Malaysia, is one of 3 companies working under the WHESSOE Asia Pacific banner and specializing in hydropower and oil and gas projects. The company believes its value lies in its unique ability to plan, manage and efficiently produce complete packages. With its long experience, the company is a market leader in the design, project management, manufacturing, construction and commissioning of hydromechanical steel structures for hydroelectric power projects and storage tanks for oil and gas terminals. Advanced piping, insulation and mechanical and electrical installations are part and parcel of services rendered. WHESSOE acts as a subcontractor to the CMI joint venture and has successfully completed similar projects for the leading joint venture partner in other parts of the world. An important feature of the contract would be WHESSOE's on-site manufacturing facility, which avoided the potentially difficult and costly transportation of the steel liners on national roads. The 5,000 square meters manufacturing facility was erected complete with overhead cranes and was operating within 3 months from the start of erection of the workshops. An active production line was soon in place. 17,000 tons of steel was imported from ThyssenKrupp in Germany and brought into South Africa through the Durban harbour. The steel plates are cut into sections, much like a pattern for tailoring or dressmaking. Oxyacetylene torches are used for the cutting. A steel rolling machine was brought from Laos after the successful completion of another similar project. The machine, using a cold bending technique and applying pressures of 2,300 pounds per square inch, can bend sections of steel plate to create a curve. These pattern sections are welded into place, creating the majority of cans with a diameter of 5,5 meters. Preheating and controlled cooling of the quenched and tempered steel is done to avoid possible weld cracking, which could affect the integrity of the linings. Manual, submerged arc and automatic methods are used in welding the rolled steel sections together to form the cans. Welds are checked for strength and integrity. The steel cans, the largest being 12 meters long and weighing up to 73 tons, are moved by overhead crane and bogies running on rails with turntables en route to the paint preparation area. Shot blasting, using a granulated material obtained from iron slag, is used to blast the metal clean, removing any oxidation and scale. An initial paint primer is then applied before 3 coats of multi-strength abrasion-resistant epoxy paint. Once painted, the cans are moved using multi-axle hydraulic trailers to lay-down areas until they are ready to be installed. The steel linings for the low-pressure headrace tunnel and high-pressure incline shafts are driven from the lay-down area to the top of the 200-meter deep surge shafts on top of the mountain about 1 kilometer from the Upper Bedford Dam. To enable the can to be lowered vertically down the surge shaft by means of an overhead gantry crane, a turning frame is attached to one end of the can. The can is then lifted and turned from its horizontal position into the vertical and lowered down the surge shaft. On reaching the bottom of the surge shaft, the can is again attached to a turning frame and slowly lowered back into a horizontal position on top of the wheeled bogies on rails. The 2 incline shafts are 50 meters apart at this point, so to access the second of the incline shafts, the bogie is driven onto a turntable, which turns the can through 90 degrees and then moved until it is adjacent to the second incline shaft, where a second turntable turns it through 90 degrees and points it in the correct direction for installation. The can is then attached to a winch with over 1.1 kilometers of wire rope and then slowly lowered on its bogies on rails which have previously been installed along the entire length of the inclined shaft. The second means of access for installation is via the main access tunnel located near the lower Bramhoek Dam. All cans for the draft tubes, high-pressure penstocks and bifurcators are installed from this point. Transport is by road on a low-bed trailer and truck tractor rig with escort vehicles fore and aft. With a high regard for safety, transporting these sections only occurs during daylight and in weather with good visibility, as the escarpment, which the De Beers Pass transcends, is prone to misty conditions. The bifurcators are massive structures where the water flow is reduced from a diameter of 5.1 meters to 3.6 meters into the penstocks that lead directly to the spiral casings of the turbines. Each bifurcator was moved to the underground site in 14 pieces, along with the all-important 150mm thick sickle plate that divides the water flow. During installation, the bifurcators sit on a temporary steel saddle, which will in time be replaced by a concrete saddle. Ultrasonic testing of the weld strength takes place continuously during the assembly and installation of the bifurcators, so ensuring that no welding flaws go unnoticed. Working safely in such a challenging environment of heavy material handling, welding, moving and installing big loads places added burdens on the project teams. WHESSOE has adhered to all safety standards and policies stipulated by Eskom and can report that no fatal accidents or incidents resulting in serious injuries has occurred on its site. As a company, WHESSOE is committed to leaving a legacy of trained personnel when it works in a foreign country, and for this purpose, the transfer of skills is paramount. Its time in South Africa has been no different, as a total of some 53 local people were trained to be machine welders, blaster painters, riggers, scaffolders and fabricators. Heavy-duty drivers were also trained and employed. The project is due for completion during 2014. WHESSOE, the logical partner for your next project.